I've been so looking forward to this talk. I think this is an area that I think is really exciting. I think it's ripe with it's a total green field. I think it's the next kind of big wave in AI, and I've spent a ton of time and energy on it, and the more time I spend, the more optimistic I become. Definitely feel free to unpause and ask questions at any point. Feel free to interrupt. It's no big deal. I know in over Zoom it can be a little bit more intimidating than in person where you can raise your hand, but don't worry about it. It's totally fine. So, I talk to a lot of people about what we do. And when I say, AI decision making or reasoning, I've talked to aides to senators, I've talked to my parents, and it always comes up this idea that I will either on purpose or unwittingly, make some Terminator robot that will, engage humanity in kinetic warfare and enslave mankind. And so I'm here to kind of spell that. A pretty analytical person, and so if you look at this objectively, I don't think that an AI, would even do this. Would try to compete with humans in some kinetic battle. I don't think that they would go up against that kind of evolution in a world that we sort of like designed for ourselves and buildings and all of that. So I think that an AI was going to some incredibly brilliant AI was going to take over the world. It would probably get some hosts to place it extremely close to the New York Stock Exchange, like as close as possible, and it would just control the stock market. I mean, that seems like the way to control humanity. That's just very conducive to AI. And so until AI is when AI is making the majority of trades on the stock market or something, then we can say they've done that. Um, and so what everyone knows is that they already make the majority of trades in the stock market, and so in a sense, we can't be guilty for something that's already happened before. I don't really look at us as wittingly or unwittingly creating the next Terminator. I actually look at us as as researchers as gaining an understanding of reasoning and decision making at a really fundamental and democratizing that and systems that are transparent, that are interpretable. And so I kind of look at us more like John Connor from the Terminator movie, people who are trying to take this technology and bring it to everybody and bring it in a way that's accessible and informative. So I asked, now that we're all working from home because of COVID, I asked my son what I do, and what my family thinks I do is actually just play Forza on my standing desk. But what I actually do is it's actually the same thing. So I think we've kind of squeezed all of the juice out of this metaphor, and we'll move on. So I've done recommender systems and personalization at a number of research labs, corporate research labs, and I've seen a lot of patterns over the years. And that's what kind of led me to Facebook was this idea of like, let's take all of these these patterns that we've seen, and let's make something really fundamental that addresses them in a really holistic way. And I currently support a team at Facebook called Reagent that attempts to do this. We've started with some domains, and we're continuing to add more, and along the way we're learning a ton, and I want to share as much of that knowledge as possible here today. Also on the side, I wrote a replacement for SSH a few years ago that I maintain called Eternal Terminal, and we have a few thousand engineers at the company using it, and worldwide, maybe like I don't know, maybe tens of thousands of engineers are using it. And I have a podcast called Programming Throwdown, where we talk about we geek out on different programming topics. And if anyone's interested in being on that podcast, definitely shoot me an email. So AI reasoning is here. I mean, the stock market is sort of kind of a canonical example of that. But even beyond that, I think now is the right time to to use AI for decision making and to apply that everywhere. I think that mom and pop restaurants can improve their menus with it. There's so many opportunities out there, and the technology is getting mature enough for us to really do that. It's definitely there at Facebook, and I'll go into that. But if you can only take one thing away from the presentation, it would be this slide. It would be that it's like this is really kind of the apex or maybe the inflection point where it gets really interesting. So what is reasoning? A lot of people know about deep learning and they know about classification. And typically you have some ground truth, like the hot dog, not hot dog app from the TV show Silicon Valley. Someone goes in and labels the data, and you assume that that person is an oracle, right? And of course, there could be error. I mean, it's an approximate algorithm, but if the person was wrong on 40% of the labels, that would be a real problem for classification, right? And so you're trying to ask this what question, right? If I show you an image that you haven't seen before, what is it? Is it a hot dog or is it not a hot dog? And the way you evaluate that is through some holdout set. On that holdout set, you don't train on it. You ask the various question, the what question, and depending on the answer, there's a variety of scoring metrics. In the case of reasoning, it's very different, right? You assume that the policy is not good. In fact, you probably assume that it's random when you first start, which is really bad. You don't have ground truth, and so you don't have like an F1 score or normalized entropy or something that's meaningful. Instead, you have to do counterfactual evaluation or offline evaluation. And in general, you're kind of asking how questions, like how could I have done this better? I mean, everyone's played chess or it could be a game or even a sport, and you kind of look back on something and say, how could I have done this differently? And that's kind of one of the most important ways that people improve. And we want to have algorithms that ask those questions as well. So at Facebook, we've primarily focused on three key areas. One is marketing. So that includes re-engagement, which means marketing to existing customers and trying to reignite their excitement about the product. Pacing for our marketing efforts. So deciding what the volume is and what the kind of spread is and the density of information is in marketing campaigns. And on coupon side, actually sort of distributing those coupons to the right people. Marketing is a really interesting problem because it's naturally very deceptive, right? Like if you give a coupon to your biggest fan, that's probably just a waste of money. Now, maybe you can get that person to spend even more potentially, but the best would be if that coupon attracted a new user, right? And so in a sense, you can see that how that's kind of a deceptive problem, right? The more excited someone is, at some point that becomes less useful to the coupon problem. And it turns out almost everything in marketing is deceptive, which is why reinforcement learning is so important. Recommender systems is also extremely important area for reasoning. And we also do a lot with infrastructure. So a lot of aspects of the data center at Facebook is controlled through reasoning systems. You can even think about your house. I mean, your house has a PID controller, most likely, or if you have a Nest or something, I think they use some other technology to control the temperature of your house. And so every house has some kind of reasoning system in it right there. And you can imagine a data center having a much more complex optimization to deal with there. So every day, and this is a very conservative estimate, probably a lot more than this, but I wanted to err on the lower bound. And so every day we make over 100 billion decisions, which is a lot. I don't think that just OpenAI Gym, a single OpenAI Gym instance will support that. There's a lot of infrastructure that goes into how we do that at scale, and we'll definitely jump into that. So, reasoning or AI decision making is kind of this umbrella term that covers a lot of different areas. I mean, here's four of them. Reinforcement learning, I'm sure we'll talk about the most today. There's also contextual bandits, which I'll explain. Bayesian optimization and even imitation learning can be considered a form of reasoning. So I'll skip through a lot of this because I'm assuming most people are familiar, but I wanted to at least cover the groundwork so that we had the common terminology. With reinforcement learning, you have this Markov decision process, right? And typically that works through being in a certain initial state, taking an action at that state, getting a reward as a consequence of taking that action at that state, and then transitioning to another state. So maybe you start with an empty go board, you place a stone. At that time, maybe you don't get a reward because the game's not over yet, but you transition to a new state that has a stone on it. And what we're trying to do is to learn the best policy. So we're trying to say, given a state and a list of possible actions, which one should I take, such that I maximize my total reward. And so in the case of Go, you likely, unless there's some reward shaping, you only get a reward at the very end. And so, a good policy is one that can look that far ahead and choose actions that's trying to maximize that final reward of winning the game. Now, there are times where you don't really have a sequential problem like that. Instead, you just have a series of decisions to make, and you still want to maximize your total value over all those decisions, but they're not. There's not a causal link between any of them, and there's and the transition. You're just kind of floating through this stream of decisions, and that's a contextual bandit. So the contextual bandit approximation says it doesn't matter what action I'm going to take. I'm going to end up in the next state and the next state and the next state regardless. And if you make that assumption, it allows you to, especially in evaluation, to do some really nice approximations. I'll skip over this. So, one kind of simple way to do policy optimization is to come up with a value function. So in the case of Go, maybe it's the probability that you win the whole game, right? If you had that function, then you would just choose the best action, right? I mean, imagine you had an oracle where for each action it would just tell you the chance you're going to win the game. You would just ask it for every possible action, choose the best one, and that would be your policy. Now, in practice, you don't have that oracle, and you're in a state of like unconscious ignorance about the model, right? You don't even necessarily know what you don't know. And so we'll typically do a softmax or some kind of stochastic policy so that we have good coverage. So we're not always taking the same action at the same state, that we're trying different things and learning from them. And so the simplest way to learn the value function is to just collect a lot of rollouts and do a regression. So I'll just look at an entire game of Go and I'll sum up all the rewards. I mean, in the case of Go, it'd be just the final reward. And then I would say, well, I played this game of Go. I took this action at this state and I won the game or I didn't. The problem with that is that you have this credit assignment issue, right? So you took many, many actions and it's not totally clear like what action caused you to win the game and what actions were irrelevant and what actions maybe were actually really bad, but you won anyways, right? So, my PhD was on playing Go, but I'm actually personally not good at Go at all. But I am tied with the world champion for tic-tac-toe. So we're gonna stick with tic-tac-toe and explore the credit assignment problem, graphically, right? So in this case, we have X, whose turn it is to move. X plays there. I mean, it seems pretty good. I mean, maybe the middle would have been better, but we'll take it. And then O moves, and then X, instead of winning the game, I mean, let's say this is the first epoch or something, X plays in the middle, which is, quite a poor move. and then O goes on to win the game. A simple value regression is going to look at all of those actions as bad, even the first two, right? And so that's the credit assignment problem, is teasing apart which actions actually caused the overall strategy to be good or bad. And so value regression is particularly brittle when it comes to that problem. But one thing you could do is, instead of summing up all those rewards and doing effectively supervised learning, you could turn this into a recurrence. And you could actually query your model at that next state and have the model tell you what the expected reward is going to be. And so you could think of this as kind of like smoothing over all the different times you've been at S prime and taken A prime, and sort of smoothing out all of those features, and getting kind of a sort of like a weighted average of that. And that in general tends to make the Q values more robust, right? But the thing that you won't get out of this is counterfactual learning, right? So in other words, it might be that in practice, the model at S prime will never take A prime. Like, the model has learned that is just not a good action to take at that time. And so you're never really going to know what would have happened if you had taken something else, right? Unless it just coincidentally happens to be in your data. And so you can ask yourself, well, if I'm querying my model anyways, why do I have to really constrain myself to A prime, right? Why don't I just try all the actions? And that's Q learning, right? So with Q learning, you ask the model what the all the action Q values are, and then you take the best one. Now, if there's a lot of actions, that could be intractable. So for places with a lot of actions, or places where the action space is continuous, we'll use policy gradient methods, right? And in the interest of time, effectively a policy gradient method is one where you find a gradient of the function that kind of connects the state to the action, gradient with respect to the reward, and you try and sort of climb in a direction that causes your expected value to go up. So two case studies that we're going to look at for kind of some real world applications of RL are re-engagement marketing and our recommender system approaches. So for re-engagement marketing, you can model it as a set of MDPs, one per person, and and people kind of go through this MDP, accumulating reward as they have good experiences on your platform. So it could be as they buy your products, it could be as they visit your website, however you have a way of quantifying what value is or what good experiences are to somebody. And at every state, you have some opportunity to send some kind of marketing material. Maybe you send an email or a push notification or what have you. So you have this binary action, should I send or should I wait? And you get a reward. And one really interesting thing to note is you get rewards at different cadences. So you immediately get a reward if you send a piece of content that is engaged by somebody. So if they actually click on the email or what have you, right? But that usually isn't the final goal of marketing, right? I mean, imagine if you were Toyota, you're not your foremost interest isn't people clicking the email, it's people buying Toyotas, right? You also have a penalty for sending, right? They presumably, it will be a nuisance if you send at the wrong time, and so there's cases where you don't want to send, and even sending at the right time causes some cognitive overhead of the person who's going to get that notification, and so you want to have some kind of penalty for that. And then you can have rewards at different cadences, so it could be daily activity, even monthly activity. And that's kind of interesting because it doesn't fit in any one of these states. And we'll talk about that later. So there's a question of how do you find that penalty, right? Now, in theory, you could learn the penalty. So you could not model the penalty explicitly and have the system just send a lot of notifications to people and then find the people who leave Facebook and or whatever the site is and figure it out. But that would be pretty a bad experience, right? And just in general, something that is a common trope with all these reasoning systems is you're going to put in guardrails based on common sense reasoning. Like there are things that you don't want to learn the hard way, and the penalty is one of those things. So what we asked the team who weren't using reinforcement learning at the time is how do you know what that is? And what they said is that they look at the volume and they try to keep the volume consistent. And so we were faced with this problem of without being able to see all the MDPs at once, how do we find out that penalty? And what we actually did was use a PID controller. So similar to your thermostat, if we find like really new and powerful and useful and valuable notifications, we'll start sending a lot, and the PID controller will kick in and say, well, the environment has changed. Now you have to be even more providing even more value to send, and it's going to keep that content relatively constant. So some of the challenges that we experienced, one is doing things at scale is really hard, and this was obvious going into it, and one of the things that we had to do is to assume the model is offline, off policy, even though it's not, right? Because with so many billions of decisions, by the time you train the next model, even if it's an hour later or a day later, you've made literally a billion decisions. And so at that point, so many things have happened that it's almost like being off policy. Um, adding structured randomization is something that people aren't used to, right? So you have to really convince people that hey, having this randomization is valuable. And of course, it's not going to be as good as taking the greedy policy right now, but it's going to teach us a lot. It's going to allow us to evaluate, and it's ultimately going to result in better performance. Dealing with distribution shifts and the effect of your policy, right? I mean, the data you're looking at was based on yesterday's policy, but tomorrow's policy could be totally different. And so it will cause the data to be totally different. And so you can potentially see these wild shifts. And so, online safety guards and retraining quite often is a good way to deal with that. And last but not least, I mean, even with any type of deep learning or really any type of machine learning, you're going to have data corruption and data integrity issues, and you want a way to autonomously catch that. We don't have normalized entropy or one of these metrics, so we have to have really good offline evaluation, and that's one thing we've really prioritized. And I think if I had to pick one thing in reagent that was executed really well and state of the art, would be that. So I'll take a little bit of a pause here. If there are any questions about reasoning for marketing or anything, I'd be happy to field something.
I have a question.
Sure.
So talking about the reasoning, so the definition of reasoning actually, in my opinion, is not very definite, or yeah, different people who have different opinions about what is reasoning. So what do you think about the reasoning? And we can see that there are many solutions of the reasoning on like recommended systems or the other AI-based systems. So what do you think about that?
Yeah, it's a great question. Yeah, I mean, yeah, it's a really, really solid question. I mean, I think, reinforcement learning is a tool. It's like, maybe the most generic and the most holistic way to solve these kind of problems, these decision making, these reasoning problems. But you might have a contextual bandit, right? Or you might have a problem where if you use a contextual bandit, you get so close to the optimal policy that it's fine, right?
Yeah,
Or even you might not even have a context at all, right?
yeah,
And so there needs to be some term that kind of can encompass all of these things, and there really isn't one. I mean, at least as far as I can see. I mean, I've seen AI decision making, I've seen reasoning. I mean, control theory is even more broad. Um, but yeah, I think you really hit on something interesting here, which is there needs to be kind of a bit of a discussion around, like, what do we call that term that encompasses many different things. I mean, the thing we don't want to do is look at the domain and say, well, you have a contextual bandit, go to the contextual bandit team or something like that, right? I mean, it's just so close to our wheelhouse. We want to ultimately we don't want to be the saw team. We want to be the team that builds houses, right?
right.
um and so that's kind of how I look at it. I look at it as, an umbrella for catching a variety of different methods, where, when you go to solve a problem, you don't necessarily know what class of the problem it is if it's something in the real world.
Yeah, thank you.
Sure. So I'll keep going, but feel free to interrupt me if anyone has anything else. So I'll do recommender systems relatively quickly. It's kind of like 5-minute abs, but for recommender systems. Um, so a recommender system typically has a funnel that looks like this. In the first phase, I mean, imagine like Amazon, for example. So in the first phase, if someone types in batteries and there's a zillion results, and so there has to be some way to narrow that down, right? And so we call it the retrieval phase. It's also called like the sublinear ranking phase, because if you have a million results, you really can't spend order and time. And so you need something that is, based on some type of index. And so matrix factorization is very good at this. Two tower models are good at this, right? Um, Actually, actor critic, believe it or not, is really good at this. And we'll talk about that. Um, then you have event prediction. So will the person click on the battery? Will they add the battery to the cart? Will they purchase the battery, right? Then based on all those events, you want to rank the items. So you want to turn all of that knowledge into a policy, right? And then post hoc, you want to do data science. So you want to do causal analysis and figure out ways to improve your website and learn more about your users, etc. And I'm going to argue that the first and the third are clearly in our domain. I mean, they're clearly control theoretic. They're clearly decision making problems. The second one is a supervised learning one, and the fourth one is in the causal arena. But the first and the third, we're the best suited area for dealing with that. And there's a lot of things that when you treat it as a control theoretic problem, that things that just show up naturally, things that are not surprises, such as explore exploit, winner take all phenomena, where a battery that was popular on the first day, maybe it was on sale or something, now becomes popular forever. Um, Dealing with slate optimization. So you're making a set of decisions that interfere with each other. Like, for example, if you show 10 batteries of all the same brand, that might not be a good idea, because if the person skipped the first one, maybe a good reason for that is they don't like that brand. And so, every subsequent decision should be inspired by, or should assume that the person wasn't happy with the decision before it, right? So a lot of these things, when you look at it through the lens of reasoning, they just become totally, totally transparent and obvious. And so here's kind of a brief framework for thinking about recommender systems. Um, you have some kind of context. So this is, the region the person is in. You continue with the battery example. It could be history of their previous battery purchases, et cetera. And you have a set of action features. So these are, the intrinsic properties of the different types of batteries you could show. You have session features. So if the person has looked at batteries, in the current session, that's really important. And then you have your event predictors. Those are those probabilities we talked about. And what most people do is what we'll call a greedy slate recommendation. So a slate is a set of actions. Think of it as like a set list. If you were a DJ making music, you would put together an entire set list of tracks, right? And the way it typically works is we'll have some kind of value function. So we'll assign a value based on those probabilities and those features to each item. The policy will be something that takes in those values and chooses the set of items. I mean, the policy for many people is just a sort, right? But as we talked about in the past, that kind of makes a lot of assumptions that could cause problems. So typically you want something more sophisticated than that, but a sort would be fine. And then you have your transition function. So at that point, the session would continue, or the person would complete the session, right? And so we kind of moved let's say the interesting part of the problem to sort of creating this value function, right? Now the value function has to encapsulate the economics and the philosophy and the utility behind whatever it is we're building. And you have a lot of challenges there when you are trying to sort of collapse everything into one number, right? You typically have a lot of guardrail metrics. So to continue the analogy, you might really not want people to return the item. And so the probability they return the item, you might want to put a hard threshold on that. So you might say, I want my total number of returns to be less than X per person or something like that. And typically, the way these value functions are created, historically, has been with what I call data scientist descent, right? So we do all this really clever machine learning, and then at the end of the day, like what I consider is like the most interesting pivotal part, we end up like doing by hand and just A/B testing a bunch of different algebraic compositions of the outputs of all of these deep learning models, right? That's a little bit sad if you think about it. So then we can move on to better data scientist descent. This is where you have sort of a parameterized algebraic formulation. So maybe it's a weighted linear sum of these events. And those weights you tune through A/B testing. So you sort of hill climb using A/B tests. So imagine you try a bunch of different values into a linear regression, or use Bayesian optimization or whatever kind of search method. And this is better, definitely. But I think even better than that would be to use a model, right? And actually learn the value function. There's a variety of different benefits that you can get from doing that. I think one of the biggest ones is that you can ask counterfactuals. So you can actually take a model that you've trained offline and predict if you'll actually sell more batteries or not. That's something that supervised learning just can't do, right? So and so three approaches for doing this. One is where you still have this, you keep the same structure. So you have an engineer or a scientist define a certain structure, and you're tuning the weights of that structure. But because you're using a model, you can actually do this counterfactual thing. So I can say, if I set the weights in this way, would I sell more batteries? And you can ask that question offline. Now, if you're going to be tuning these weights and you have this offline analysis, then you might as well open it up and and have a deep net create the value model directly. So take in all these event predictors, these features, and just learn the value model, right? And then, what you might say is the holy grail or something that's like even more powerful would be to do policy gradient on the slate. And so in this case, you don't even have a value model. Instead, you're just saying, here's my context, and here's the list of items that I want to show to the person. And that, is the most open-ended, and it will be truly like a DJ. When a DJ composes a set list, they look at all the items and how they flow into each other, and they create something that's smooth. And policy gradient over the whole session or over the whole slate will let you do the same thing. So some challenges that we found, there's a lot of challenges, a lot of lessons learned, and it's been an extremely valuable experience. So the first is, how do you do randomization with ranking in a structured way? And we had a paper on this a while back, but we use a trick where there's a distribution called Frechet. It's also called log Gumbel. And when you multiply two Frechet distributed numbers, you get another Frechet distributed number, which is extremely convenient because when you're ranking, you're making a set of decisions in sequence. And so the probability of that entire set, you now have a closed form for it. So as opposed to, originally we were doing just, a soft max, kick that item out, do another soft max. Well, if you do it that way, there's no closed form. Here we have a nice closed form. And so that helped us tremendously. One of the biggest challenges is there's going to be that business logic similar to the past domain, where you're not going to have a total green field where you can try all sorts of things that could be really odd for an end user, right? And so you can either treat those downstream actions as noise. So, it's kind of like if you're playing Go, but every now and then someone bumps your hand and you end up placing a stone not where you wanted, right? So you can either say, well, that's part of the reward. Sometimes they're just going to lose some Go games, almost like exploration. Another way to do it, which we haven't done yet, but I think is really powerful, is to actually just have a framework for implementing that business logic such that you can run it at training time. And so whatever people are doing downstream is done at training. And now the training loop is kind of aware of those changes. To deal with a lot of the guardrail metrics, like the returned batteries, we're spending a lot of time and energy on RL with constraints and handling that, especially constraints that span, the entire set of episodes, right? And another challenge is that you might get, if your goal is to maximize X, you might have a million different policies that maximize X, but they all do wildly different things. And the people who are looking at those policies are going to see that difference, even though with respect to X, your reward, they're all the same. And so people just say, wow, like, I'm looking at this other metric that's not in your model, and it's just wild. Every day it's totally different. And so one way to do that is to fix that is to start with some behavior cloning. And at least you kind of bias the model in the direction of the model that came before it. So I'll take a little bit of a pause. If anyone has any questions about RL for Rexus.
I have a question.
Sure.
Yes, when you do slate recommendations by reinforcement learning, and do you consider the diversity of the set of recommendations, and how do you consider the diversity during?
Yeah, that's a really, really good question. So, yeah, so a couple of things to say about that. One, it might be just organic, right? So, if a diverse set of content is just better, right? If you're going to get a better reward for that entire slate, then the problem will solve itself, right? Um, I think in practice, well, one of the things you want to do is to measure the diversity. So you want to have some kind of metric that says, did this set of recommendations have more or less diversity than this other one? And as soon as you have that metric, you could say, well, I might be willing to sacrifice some utility to have more diverse content. Again, assuming that maybe that's a hard thing for the model to capture automatically, right? And so, I don't totally remember if diversity is manually added or not, but I know we've talked about it. And yeah, the first step is measuring, and then once you measure, then you can always optimize. Cool. So we'll jump into how to do this at scale. One of the things that I kind of hinted at earlier is to treat it as a kind of a batch problem, right? And so that causes a number of issues. I mean, one, you want to have a really good model every time. Like every time you update the policy, even the first time, you want the new policy to be good. So a lot of the things we know from deep learning still apply. You need to have good normalization, and you need to have good regularization, a relatively low learning rate, things like that. We want to do distributed training because we're training on a lot of data. And at the end, having an online, training is not practical for a lot of reasons. I mean, it would make the on-call very problematic. It would require some extremely complicated infrastructure that, frankly, I have no idea how that would work. And so we want to have fixed policies, but we want them to be stochastic. And so you can imagine sort of baking this idea of there being E greedy or epsilon greedy or softmax or what have you into the policy. And so the policy gets containerized and shipped out, but in that container there is some noise and some randomness. And last but not least, you want to have really, really solid offline evaluation so that you can, if there's some corruption in the data, you can send an email and say, hey, I really don't think we're going to sell so many batteries with this model. You should probably not ship it. You want to have that capability. And the way to do that is to have a tight loop. So the serving part and the training have to work together, which, depending on your company, that might be really unorthodox. Like it might be, generally the serving folks, they treat the model as a black box. So they say, our job is to just do the forward passes model, as robustly as possible. But that actually won't work, right, for control loops. I mean, they're going to have to understand the model, or they're going to have a really expressive serving infrastructure that can allow the folks building the model to actually do exploration and do those things at the serving layer. And so, one thing we've provided with the open source repository is a serving platform, which, internally the serving, we work with a lot of different teams. And so this is part of a bigger system internally. But from the open source side, it's totally end-to-end and self-contained. And on the website, there's a tutorial that walks through how to create a decision plan that includes sort of the exploration strategy and how to ship that to RASP and execute it. The training flow is relatively straightforward. I mean, the only thing that's a little different is we do support for unit tests. We support OpenAI Gym and other sort of simulation based. And now there's even some folks who are using Reagent in an online way because they have high fidelity simulators. And so we added support for that as well. There's many different ways to do off policy evaluation. But the thing that I really wanted to point out is going back to that bandit assumption, right? If you can assume that your action has no consequence on the next state, then you can get a much more accurate policy evaluation, right? Because you don't have to you hallucinate, right? You don't have to imagine states that don't exist in your data. And so generally for any problem, we'll return both of these evaluation results, and people can look at that qualitatively and decide what they want to do. So yeah, on the horizon, I mean, we want to take a look at DICE. So DICE is a really attractive idea. It's where you don't even have to know what the logged policy is really doing. You could kind of infer it from the data. In practice, we found it pretty difficult to behave properly, but it's something we're still looking at. Another challenge is, if you look at Go, you get a reward at the end, but all the decisions, had an impact in that, right? They're all causally linked to each other. If you change one, it's going to massively change the game, right? Especially in the beginning. But you might not have that. Like you might have a situation where maybe 4 decisions are made where they're not causally linked to each other. I mean, imagine going back to the marketing example, maybe there's 4 marketing decisions you make before you get any feedback from the first one. And so there's no causal link there. And so just doing Q learning and back propagating actually creates is not sort of the correct way to model that actually. And so we're looking a lot into how to deal with that problem. Another thing is, because we have so many inferences of the model between training cycles, we're looking at some of these offline or batch RL approaches, and I think we could get some better safety guarantees out of them, even though we are technically on policy. I think using these algorithms will actually help keep the model on track. So that's what I got. I believe we have about maybe 8 to 10 minutes. So people feel free to ask me anything. I'd be happy to add some more color.
Okay, thanks for the great talk, Jason. I think if you click the channel chat channel, there is a question for you.
Oh, cool. Oh, how do you construct the environment and the reward for training? Yeah, it's a great question. So yeah, at a high level, you're kind of moving the problem for people. So people might be doing data scientist descent on the policy, right? And in a sense, you're moving them towards doing data scientist descent on the reward, right? And so one could, be critical of that and say, well, did you really provide any value? What we've found is that it's just much easier to do the latter. Like people just intuitively think of the utility of something. It's very unintuitive to think about the policy. And when we look at policies that have been crafted by hand, especially ones that have evolved over years, the units are completely, arbitrary, and it's kind of bonkers. Versus the utility, it's just much more natural. So you're right. So once someone is, using reagents, so for people on at Facebook who have been using it for years now, they're in the business of trying different reward functions and learning the sort of Pareto front. So if I trade this metric for that metric, how much do I get of that one for the other one, right? Or they'll invent a new metric, a new way of looking at their problem, and so that's where most people will spend their time once the system kind of reaches maturity.
Okay, thanks for your question. Thanks for your answer. Any other questions from the audience? Actually, I have a question. I remember you mentioned that when we do the reasoning, there are some models such as reinforcement learning, bandit, imitation learnings, these kind of things. what's the difference, and could you compare their models and the performance?
Yeah, it's a really good question. Actually, something that I didn't include in the deck, but we have something called the domain analysis tool. And this is something where we look at a large data set, a large output of a policy, and we try to guess, is it a bandit? Is it a reinforcement learning problem? We can even find out it's not even like a problem we can solve. Maybe like there's no correlation between the state action and the reward that we can find. So we'll run this domain analysis tool, and it will spit out a bunch of information. It will also construct a world model, and from that world model, it will infer which features are important. So a feature might be important to the reward, another one might not be important to the reward, but important to the transition. And so if we're doing DQN, we're not explicitly modeling the transition, but of course it's very important. So so the domain analysis tool is what we'll use to inform people about that. But at a high level, the contextual bandit assumption is very, very convenient, to the point where, even if people feel like coupon is a good example, people might say, well, if I send someone a coupon, that's going to change their behavior. And so maybe that's more of an RL problem. But like the question is then, like, are you really sending multiple coupons to the same person? And if the answer is not very often, then the contextual bandit approximation, will work really well there. And even though you might leave some part of the problem on the table, what you get back is much lower variance and much more control over the problem domain. I think when you look at, let's say, Bayesian optimization or just search in general, definitely searching through the policy has a lot of attractive properties. Like you can do an A/B test and you can know for sure, like, this policy is better than this one. I don't have to guess, like, I'm just sure of it. And you can hill climb in a very confident way. But it's extremely expensive. And so doing a Bayesian optimization over, millions of parameters, even if, forget the computational part of it, it's just intractable if you have to run an A/B test to collect a sample, right?
Yeah.
So that's sort of where how to trade off, that method. And behavior cloning is in general just a really good way to start. I mean, whether you're starting a new model or even if you're starting recurring training, your nth model, warm starting the model or starting by cloning the existing model, puts you in a really nice space. There's a lot of qualitative value in these things. And so you might train a policy, like someone might tell you, I want to maximize X. And you train a policy that gives them 2X. But then like a whole bunch of other things go wrong. And they say, oh, no, actually, here's like 10 other things that really matter to me. And if you start with behavior cloning, you minimize that, which is extremely, convenient.
Okay, thank you.
Yeah, sure.
Any other questions? Okay, if no questions, let's thanks to our speaker. Thank you, Jason, for the great talk.
Cool. Yeah, thanks. And if you have any other questions or anything pops in your mind, just shoot me an email. I'll be happy to answer anything.
Okay, thank you. Okay, I think the next talk is the first paper talk from Shuang Li. She is from Baidu. Shuang Li.
Hello.
Hi.
Yeah, okay.
Yes, we can hear you.
Okay. I need to share the screen.
Yes.
Can see it?
Yes.
Okay. Now let's begin. Okay. Good morning, everyone. I'm Shuangli from Baidu, China. Glad to be here to present our work optimizing and pruning of sponsored search with reinforcement learning. This is the outline of this presentation. First, let me make a simple introduction of sponsored search. I think it's known to everyone. Okay. Web search engine plays a vital role in our daily life. For seeking information, sponsored search is to place a sponsored result among with the organic search result. Since the submitted queries will express a clear intent, search engines provide a good platform for advertisers to accurately target clients. On this platform, advertisers need to submit keywords, bids, and creatives for their products and services. A keyword is a short text to be matched towards query traffic, which can be seen as a bridge to link queries and ads. A creative is some text that would be shown to users, which generally includes a title and a description. In the sponsored search system, there are three main modules. First is the keyword matching, and then the ad retrieving and ad ranking. When a query is issued, the keyword matching module would retrieve all the semantically related keywords, and the ad retrieving module would retrieve all the ads of the advertisers who have bought the keywords and filter out some conflicted ones and equip them with compatible styles. Then these fully equipped ads would be gathered to go through the ranking module, where lots of module predictions like click-through rate, relevancy, and filter rules are conducted. And an auction is carried out for the remaining ads, and the final winner ads would be shown to the users. A serious problem during the ad retrieving is that the candidates grow rapidly. For example, a query with high commercial value can retrieve 100 to 1,000 even more matching keywords. Each keyword may be bought by 10 advertisers, and each advertiser might design 10 different creatives for this unit, and 10 different display styles can be chosen. That is, we would get the fifth pair of 10 candidates or more candidates in this case. Directly sending this ads to the ranking module would consume a lot of computation time, which is unacceptable for an industry online system. One solution is to prune the ad candidates earlier during their expansion. Here we set our pruning line between expanding the creatives and expanding the styles. Then a typical ad selection problem is how to select key items from any candidates to feed into the downstream system so that the total revenue can be maximized. There are several challenges for this problem. First, the real industry downstream system is very complicated, which really deals with an click-through rate prediction, blacklist filter, diversity filter, ad quality checking, and so on. Without considering the downstream system, ads selected earlier might be filtered out a lot. Secondly, at the current moment, the ad candidate is not complete yet, such as the style information is not available yet. Thus, we can't obtain a precise click-through rate estimation here, which is a key element for winning the auction. Thirdly, this is an NP-hard combinatorial optimization problem. Some heuristic approaches are widely employed for tackling this problem, such as sorting all the candidates under the revenue estimation and selecting the top key items. Obvious disadvantages of this kind of solution are that It is impossible to design a perfect rule due to the sheer complexity of the downstream system. And the quality of the whole selection system, such as diversity, are easily overlooked. Even if we adopt supervised learning-based deep neural networks to solve it, it is hard to perform well as we are lack of the best training samples. In this paper, we resort to a reinforcement learning approach, where the ad selector is the agent and the downstream system is the environment. The agent sequentially selects key items and feeds ad Q into the downstream system. The downstream system would return the final revenue for the ad Q, and this revenue would be taken as a reward signal to guide the selection policy. The advantage includes that, firstly, use a model-free learning framework. The complex downstream system can be considered as a black box environment. Second, we don't have to rely on labeled data. We can make trials based on the rewards. Thirdly, with the exploration of reinforcement learning, we can try to achieve the best result. The specific problem formulation is shown here. The state comprises of the selected ads and the unselected ads, and the action is to select the one ad from the unselected set. The whole sequential decision process is to select one ad from the unselected set until key ads are selected. In particular, a Markov decision process is defined here. For example, for each step, the state variable S occupies the current unselected ad slate as well as the already selected ad list. All ads in these two lists are drawn from the original set. At start time, the unselected ad set equals to the original input, while the selected ad set is empty. Based on the current set, each action A is to choose one candidate ad from the unselected list and append it to the selected list. The policy of our agent is a selection probability distribution over the whole unselected candidate set. It is approximated by a neural network parameterized by theta and denoted by pi theta. When the selection is finished, this key as in Y would be sent to the downstream system for further ranking and auction, and finally as one out would be shown to the users. The objective function we are going to optimize is the typical objective in policy gradient. We use the policy gradient method to do our optimization. And in this section we made a few modification to the original algorithm. About the rewards, there are several tricks in our work. First, in our scenario, the reward is set according to the estimated CPM contributions that is estimated rather than the actual CPM. It is because that doing an exploring algorithm on the online system is of risk. Secondly, the reward for selecting an unshown ad is set to 0. That is reasonable. Thirdly, since the estimated CPM differs a lot among different ads, to reduce this variance, logarithm transformation is adopted to smooth the original estimated CPM. So the instant reward is formulated as the formula here. And in our experiment, the training speed with the logarithm transformed reward is much faster than before. The right figure is the simulator we construct to get reward from the downstream system. The clue is that the whole simulating system is cloned from the online true environment to make the traffic is real and the reward is same as the online system. This page demonstrates on our network and feature engineering. The model to approximate the candidate at selection score at each step is a two-layer fully connected network. Final selection probabilities are obtained through a softmax layer. Being represented with the design features, each of the unselected ads would go through the full connected neural network, and their outputs would go through a softmax layer to get the policy distribution. The parameters of the neural networks are shared for all of the ads. For the ad features, main features are shown here. These features can be grouped into two categories, static and dynamic. Static features do not change as the selection process. For example, each ad has a bid, semantic matching degree with the query, click-through rate, estimated CPM, and so on. And the dynamic features changes with the selection process. It is designed according to the system consideration, such as some common ads belonging to the same advertiser should not be displayed at the same time. It means that advertiser would compete with himself. So we have to control the ad numbers belong to the same advertiser. The typical two dynamic features are shown here. And the training algorithm is shown here, is also listed in the paper, we skip it. Finally, it's the result. We compare our approach with two baselines. They are commonly used in industry and are also adopted in our sponsored search system before this IR method. The first ranking baseline is by expected charge by the advertiser, which equals to estimated click-through rate times bid. The second is ranked by estimated achievement from the downstream system, which is calculated by expected charge times the show probability. The show probability, SRQ here. The show probability is added due to the limited advertising possession and multiple factors affect the eventual show results. Here we approximated the show probability of an ad to its accumulated show proportion in the past 30 days. And the three most important indicators of our methods are compared with the baselines. The results demonstrate that our method achieved positive improvement over all three considered indicators with both baselines. Considering that the ad supplies are stable, the increment in shows shows that our agent does select better ad candidates which are more compatible with the downstream system. In addition, the proposed method also gains significant CTR improvement. It denotes that the newly shown ads are greatly accepted by the users. Owing to the consistency of our planning agent and the downstream system, as well as the end user preference, we finally achieved about 1 percentage improvement of CPM. In other words, it's a good result even for now. And this is our framework for applying IL in our sponsored system. Thank you.
Okay, thanks for the great talk. Any questions from the audience?
Yeah, hello. I have a question. So, like, how do you train your like this sequence decision model? Do you train online? Like let the model improve by itself in an online setting, or anything else?
In fact, we treat it not fully online. We construct on a simulated system. The system is similar, almost the same as the online system. The difference is that we want to show that the traffic is similar to the real traffic. the difference is that we won't show the result to the true users and get the click and other feedbacks from the users and use the charge like that. We only use the estimated revenue from the downstream system. That is, we truly believe the downstream system. It is to do doing so. It is because if we doing an exploration policy online, it will do harm to our online system.
Yeah, thank you. So, but when you report the results, you said like you have some improvement over existing methods. Like that's where you that's when you test your model in the real product.
Yeah.
System,
yeah.
right?
The result is when we train a stable model, we will update this model online and make a and we won't make a exploration. Then we will only exploit, and the result is tested on the version.
Got it. So, is there any efficiency concern about this model, or is this model like officially launched into your system?
Innovation, you see, our model is in fact not that complex. It's only a two-layered network, and we made a lot of work on our feature engineering, and the online system cost is okay, I think.
Okay. So has it been launched to your system?
Yep. Yeah.
Okay. Got it. Thank you.
Okay, any other questions? I have questions. I think in your state, you consider both the selected and unselected advertisement. So what's the number of the selected ones and the unselected ones? And how do you handle the, I mean, whether it's balanced, whether the selected ones will be buried by the unselected ones?
I don't get you.
Yes, I think, I mean, in your state of the reinforcement learning, you define the state incorporate both the selected advertisement and the unselected advertisement. I mean, what's the number of them?
In our online system, not online system, it's about 1,000 candidates and select 100 like that.
Okay, so probably you have much more unselected advertisement than the selected ones, right?
Yes,
so
this is unselected as in our online system. In fact, we will append them to the list and won't get their sequence. And the top selected results are arranged, sorted, excellent. And the long tail results, we will be just skip them.
Okay, thank you. Okay. Actually, I have another question. What's the model you use for your simulator?
Model?
Yes, what kind of model you use for the simulator? Just a two-layer MLP or other models?
Yeah, just a two-layer MLP.
Okay.
So the main work is at the features, I think.
Okay. So, any other questions? Okay, if no other questions, thanks for our speaker. Thanks, Shuang. Thanks for your great talk. Okay, thank you. I think we can have a 10-minute break and we can come back at 10:30 in Beijing time. Okay, see you later. Okay, welcome back to our workshop. In the second session of our workshop, I think we have one keynote and one paper presentation. The first is the keynote from Dr. Yuxi Li. Dr. Li is the author of the well-known 115-page deep reinforcement learning overview history, and he is writing a book about deep reinforcement learning applications. He is the lead guest editor of a machine learning special issue and the lead co-chairs for several workshops on reinforcement learning for real life. And he has published referred papers at venues such as NeurIPS, Status, and Infocom. And he served as the TPC members and reviewers for conference and journals like III, ACM Computing Survey, TKDD, and PLOS ONE. He obtained the PhD from the University of Alberta, and he was a postdoc here, and he was an associate professor in China and a senior data scientist in the US. He founded the Attain AI in Canada. Okay, Dr. Li, it's for yours now.
Okay, thank you for the invitation. It's my pleasure to share my understanding about reinforcement learning applications with you. Actually, this basically a big survey of this area. Is actually, you can see that there will be many pages. So yeah, hopefully I can give you a glimpse of what's happening and what may be the opportunities and challenges for this reinforcement learning applications. And in some cases, maybe we can they are related to knowledge discovery in some sense. But you know, knowledge discovery is a general term, so it will be actually everywhere for AI system. Oh. Yeah, so AlphaGo reinforcement learning. This wave of reinforcement learning is basically started from AlphaGo, and yeah, so I don't need to say too much about it in 2016. And yeah, this is a one slide instruction about reinforcement learning. I believe many people in the workshop are familiar with it. You know, we have agent interact with the environment from state to state, take some action and go to next state and receive a reward. And we want to maximize some long-term reward. Actually, this reinforcement learning, this reinforcement is from classical conditioning. People know this Pavlov's experiment with the dog and food. Reinforcement learning is related to many fields, like say optimal control, like optimal research, like say economics, computer science, psychology. Yeah, people may know that Reed Sutton, his bachelor is from Stanford with psychology. So maybe that's one reason reinforcement learning has some, the psychology and neuroscience has some influence on reinforcement learning. Yeah, this is basically about the relationship about those terms. This is an academic conference, so actually this slide was prepared for actually many audiences, and for this academic audience, I don't think I need to talk about this the relationship about these terms. Yeah, there is a hypothesis by David Silver. He said that something like reinforcement learning and deep learning is AI. So we want to say that reinforcement learning is very promising. And yeah, I believe people will debate about this hypothesis, but in some sense, it makes sense. Even Russell and Novick in the textbook, they basically say reinforcement learning is basically everywhere in AI, and yeah, so but it's debatable. Some people may not agree with this. Recently, you may know that reinforcement learning basically many achievements are done on games, and in particular the Atari games. And in this way, is basically the DQN, the Deep Q network, ignited this wave of reinforcement learning, in particular deep reinforcement learning. And during the last several years, there were lots of achievement. And in last year, there was a paper called Agent 57. Basically, it achieved human level performance on all the 57 games. Yeah, better than human being. And on a fifth percentile, the metrics, performance metrics was fifth percentile. Yeah, before this, people use average. You know, average sometimes may hide something, but fifth percentile is, you know, considering the worst fifth percentage of performance. So it can, if we have better results for the fifth percentile, then we basically how, yeah, is you know, it's kind of the worst case analysis. So I think I highly recommend this paper. I think it's yeah, I didn't mention in this talk that reinforcement learning, you know, it can be value-based, can be policy-based. And this paper, I think, is a very good summary of the recent progress, and it's a good integration of those technologies. From this figure is from the DeepMind blog. Lots of those components, they combine them into the paper and make the system work. So if you want to, especially if you want to follow the value function-based approach, then this paper is a very good summary of the recent progress. Yeah, another paper, similarly, same time, they achieve pretty good results on the Atari games, and they are even better than the Agent 57. So, and they are published in Nature this year. And AlphaGo, so yeah, AlphaGo, basically deep learning, reinforcement learning, and Markov research. It's a big news, and there are lots of details. So in case somebody interested, I can discuss this, answer questions. And yeah, I put many games here, like the StarCraft, like poker, like curling, like Dota, like something called this is catch a flag and hidden seek. So so people have achieved very good results on those games. So when we talk about games, you know, games can be abstract for many problems in AI in real life, and the potential applications of techniques in those papers, you know, I list them here. Basically, they are everywhere. For example, if we pick something like, say, classical planning, like scheduling, you know, these are very general terms. So they can be in many places, say planning problem and scheduling problem. And once we can solve something like Go, like poker, then we can solve many problems, probably. So that's very promising area for reinforcement learning. So games to AI is like fruit flies to genetics. It is said by Dr. but I think we can understand it just like the games are good abstractions of many real life problems. And something called reality is broken. In Chinese, it basically says the games can change the world. So you know, many things we can gamify them. For example, a couple they may fight about who will watch the dishes, but if we can create a game for them, then they can follow the game, and if somebody loses the game, then he or she will watch the dishes. So we can gamify many things. For example, education. For example, in workplace. Actually, yeah, in workplace, for example, the salary or the dividend. Yeah, these options. These are kind of the incentive. So they are basically following some game strategy. Yeah, just now I gave a very brief introduction of reinforcement learning of some very successful applications. I will like I said, this is a big survey of this field of reinforcement learning applications. So I'll go over next. I will go over many successful applications very quickly, and then after that I will talk about challenges and opportunities. Yeah, multi-unbounded. Basically is there are several options, and we want to pick the best, but we don't know the underlying distribution. So people have applied it to many problems. For example, in Microsoft, they apply to say click-through rate for say landing pages, and they achieve actually double-digit performance improvement. So that's great. Actually, this multi-unbounded, they can be applied to many applications. For example, for news website recommendation, for tech support assistant, for crowd controller, for many. Since it's an abstract model, so it can be applied many places. Yeah, this is basically the model for the bounded. This is the detail of that results. So Microsoft, they actually this paper although there are good work. For example, Jason just talked about the work in Facebook, horizon or reagent. That's pretty good. I mentioned this paper. One reason is when we want to make something realistic, we want to build software system. So we face the software system issues, and machine learning, reinforcement learning in particular, they are much harder than traditional software. And in this work, they talk about how to deal with some failures and something called technical dice, and they propose some abstraction to do those things. So yeah, if you are interested, there's a paper on open source. You can check them. And also from Microsoft, they applied the contextual bounded learning to a customer support bot, and they summarize some lessons. And yeah, it's also from paper. So basically, I won't say this again. I will mention many applications. If you are interested, you'll check the papers. I will probably just say the title to you. Again, Microsoft. This is basically from a blog. So it's a summary of the recent progress of reinforcement learning applications at Microsoft. And Rexim is from Google. They built a model, a recommended simulation for recommender systems. And yeah, it's from Google. But I also put actually, the organizer of this workshop, for example, Xiangyu, Dawei, Long, and Ji Liang, they have published many papers on recommender systems, in particular with reinforcement learning. So they already done lots of work. So if you are interested, check their work. And also for the recommendation, say from Google, from Microsoft, from Facebook. Yeah, Justin has just gave a talk, so I shouldn't say too much about this. And this one I think is also exciting one. It's from another big area, operation research. So operation research, there are lots of decisions to make, and that's a traditional area, and people need to make decisions in. For example, for this case, it's for DD, and but there are many cases for example, in the manufacture, in the industry, in say classroom classes, scheduling. Yeah, many cases, and I think DD, they have done pretty good work, and they achieve some great reward from the ORMS, operation research and the management system community. So that's pretty exciting for, I think, for reinforcement learning. And this one is from Google and a small company acquired by Google Loon. They use reinforcement learning to navigate the stratosphere balloon. It makes work, and I think that's great. But sadly, there was a news about that this project was terminated. So you know, for referral learning to work, there are many issues, technical wise, non-technical issues. So later I will talk more about this. You know, why referral learning is not widely, you know, especially comparing with deep learning. This one is also very interesting. It's about quadrupedal locomotion over challenging terrain by a robot. It's a real robot, and they are you know, using some recent techniques, for example, imitation learning and you know, real to life, those techniques to make this robot controlled by a reinforcement learning to work pretty well. This one is about computer system. You can see from the leftmost column, you can see many environment from video streaming, cluster job scheduling to SQL to circuit design to server load balancing to account region assignment. You know, this basically runs the from the very bottom to the very top of computer systems. You know, for computer systems, you know, there are many decisions, and you know, reinforcement learning is for decisions. So reinforcement learning has the potential to work in many of those problems. Yeah, I also put these. I think all of them are from Google. This for neural active search. This from augmentation for, you know, data set, and this is for device placement. For, you know, for the say I have a TensorFlow program. I want to run this program on, say, GPUs, CPUs, and memory. How to allocate this program to those devices. And the bottom one is about circuit design, chip placement. There is something I think very exciting about is it doesn't use reinforcement learning yet, but reinforcement learning will be helpful sometime. So it's about AutoML. It's learning machine learning algorithm from scratch. I think that's, you know, it's kind of amazing, right? We can even learn those, you know, for the neural architecture search, we can learn them for a given data set, we can learn the best neural architecture for it. And now we say people extended to learning machine learning algorithms themselves, and maybe I think probably some techniques can help identify the best algorithms. You know, something just like, you know, for AlphaGo, we are learning from scratch. We don't need any prior knowledge. We just learn from scratch. We just know the rules, but we can, you know, learn, say, using self-play or those techniques. And this time, people have already done great things for the machine learning algorithms themselves. Yeah, and recently there are work about combinatory optimizations. And actually, just now we mentioned something. There are the underlying problems. Some of them are actually big combinatorial optimization problems, and people also, you know, study this specifically. For example, especially for some classical problems like vehicle routing problem, and people have already achieved good results. For example, comparing with traditional OR approaches, reinforcement learning can achieve better results. Yeah, this one for traffic, for, say, autonomous driving, it's a environment, it's a simulation environment. And this one for game testing. You know, game testing or software testing, I think, you know, these are it takes lots of people, lots of energy to do those tasks. And say reinforcement learning has done some work for, say, game testing, and it's also possible for software testing. And for education, for instructional sequencing, so reinforcement learning, yeah, how achieve good results. And this is for intrinsic motivation. And we try to build education system and education game, and try to, you know, using some underlying psychology, underlying principle, like intrinsic motivation, and try to make it fun to people using it. You know, especially those young kids. And yeah, there's a theory from psychology called flow, and this one is basically, you know, close to that, related to the flow and intrinsic motivation. They are in some sense related, and I think that's one way to help build how to build the, say, reward function. Well, you know, when we want to say automate something, for example, game design, we want to automate the content. So why the content is good, how to judge it, how to evaluate it. So we need some measure, we need some metric, and say some psychology principle can help to this. For example, say people can define this fun using some theory from psychology, and if we are following those some principle way, then we can, you know, for the learning, we need state, action, reward. We need those definitions, and if we have those definitions, and yes, sometimes state and actions are not so hard, but how to design your function, that's just like Jason mentioned just now. You know, your function is difficult to define, and if we can use some psychology principle to define those reward, for example, fun, then we can build a system using reinforcement learning, and we can create the game content fun for people. And also there are also work for healthcare, and you know, there are some terms like macro randomized trial, like just-in-time adaptive interventions. Yeah, and also for finance, there's a simulator. They build some yeah, they open source this. So if you are interested in finance, so this is a one source. Yeah, and yeah, this is the yeah. Okay, yeah, this one actually this is a paper, and this is the simulator. This is the open source, so you can check that FinR. And this one is for the AI economics. AI economists, they built some system to do the to evaluate tax policies. And this is for data center cooling. You know, this touches the traditional control systems, and so I also list you know, the MDP, MPC, model predict control. That's a popular approach in control systems, and reinforcement learning in this case can help do the exploration. So learning basically from scratch, but it can improve the performance and better than say MPC, than PID. So this is from this is from Google. They tested on their data center, you know, the big data center. Yeah, so I think there are people now talking about say reinforcement learning, about say operation research, about optimal control. I think that's very good. You know, these terms, I think they are basically highly related, and so I think maybe they are merging. So yeah, there's a work about, you know, this is a simulator for reinforcement learning for the electricity distribution system. It's about you know, energy system. And okay, there's another is from drug design. I think this is very interesting. Actually, I realized this problem several years ago, but just after the news about AlphaGo. But one reason I didn't spend too much is I don't have much background in say biology and chemistry, but I think this area is pretty promising. If I want to work on this, I need some good collaborator for this, but I think that's possible. Yeah, this is AlphaFold. This is a big news. So far, it has not used reinforcement yet, but reinforcement probably will be helpful for AlphaFold, for for drug design, for AlphaFold, for something in chemistry called retrosynthesis. I think for these problems, they are somewhat close to AlphaGo, to the Go problem. They have very big search space, and they want to try to reduce the search space. And for example, for drug design, they want to come up with some good candidate. So if they want to do more lab testing, it reduces the cost. But the reinforcement learning can help reduce these candidates. That's a very big saving. Also for AlphaFold and for the chemical resource synthesis. Yeah, calculating, I think that's very interesting work. I even spent several months on this, but just currently I'm a small company. That's probably not for a small company unless there's a good funding from the government or somewhere. Yeah, but I think reinforcement learning should be very promising for this COVID-19. If you're interested, I have a document, manuscript on my webpage, attain.ai. If you are interested, welcome to check it. Yeah, next I will talk about the challenges and opportunities. I don't know, maybe I'll go until the end and then ask questions. But maybe take a break. If somebody wants to ask questions, please go ahead. Yeah, but I know I just just touch too many topics. So okay. Now let's talk about challenges and opportunities. I think the first challenge is we mentioned that before. Machine learning system is a software system, and so far I think there are some work in the machine learning community. They study this system, and in the traditional software system we have pipeline. We have say requirement, and then following the requirement we can build model for the software system. We can build the software system, and we can test it and we deploy it. This kind of pipeline, but for machine learning it will become very messy. There will be loops in those components. So for example, when we go to the model evaluation stage, we see that the model doesn't work so well. So what may be wrong? Do we need more data? Do we need to have a better feature engineering? Or even, is the model requirement is good enough? Do we want to fix it? So we may go back to the very beginning for the machine learning system. So it makes this very entangled and very messy. So for machine learning systems, we need to think about those problems. We want to find good ways for building this kind of machine learning system. And this is for machine learning, but for reinforcement learning, the problem may be even harder. Just like we mentioned that before. For example, the data. For example, for reinforcement learning, the data is basically like state, action, reward, next state. So the reward may come much later. So in the software system, we need to make sure the reward comes together with those state, action, reward, next state. So we have a one piece of data. So when we build system, we need to consider those things. So we need some new software engineering principles to deal with machine learning, in particular our problems. Yeah, and there were discussions about the technical debt in the machine learning systems, and I think that's great. People have done some work on machine learning software system deployment, those problems, and there is already an overview about those problems, and you can see it's about the deployment stages about software machine learning software systems. So I think, one thing is we want to, I think that's probably an interesting topic for the community. It may span several communities. For example, software system, for example, machine learning, reinforcement in particular. So we want to build we want to have some more suitable software engineering principles for reinforcement learning. And also, for the deep learning, one factor is we have very good data set, for example, ImageNet. But how about reinforcement learning? So we may want to build some good data set for reinforcement learning. And recently, people are talking about offline. So that's interesting. And yeah, there are some say our competitions. For example, for the Amazon AWS Deep Research League, there are something about twins. There are about the dispatch and the reposition on for the red herring, and they are also for the power network challenge and also for autonomous driving. These are good things. So from those, we can collect more realistic data for reinforcement algorithm to train. And so yeah, so that will be very helpful. Yeah, I put this here. One reason is so this is about from the title you can see it's about motivation, about engagement, about thriving in the user experience. So it's about user interface, and this from yeah, I spent several months studying the psychology. Just now I mentioned intrinsic motivation. I mentioned flow, and this one is about self-motivation theory. They are somehow related, and I think all of them are part of the, especially flow and this self-motivation theory. They are part of the something called positive psychology. And for this, in particular, it's about UI. I think there are basically two angles. One thing is we want to apply those psychological principles to design UI. Another thing is we may want to use those psychology principles to design reward and to help automate this kind of design. So you know what I mean, right? So one thing is we want to use those principles to design better UI. Another is we may using those psychology principles to help, for example, design the reward function and then to automate the design of those UI. So I think that's interesting area to check. So I put this here. Okay, there is another topic is about challenges of real world IR. So there's recently a paper. It was in our 2019 workshop, and recently, we are editing a special issue for machine learning journal, and this one is already accepted. So far, I think it's yeah, it's very close. Maybe in 1 month or so, it will be become public. But at this time, if you are interested, you can check their archive version. They summarize, I think, is 9 challenges, and they talk about mainly for, I think, continuous action space, for example, robotic systems. But I think many problems, for example, high dimensional state and action spaces, is also applied to, for example, RAG systems or say knowledge discovery problems. And so I think it's at least informative, those kind of challenges. Yeah, and they for sure they will talk about the state of art of those, and they recommend how to handle those kind of challenges. So people gave some suggestions about the foundation of efficient robot learning. Talk about sample efficient, talk about generalization, talk about composition, talk about incremental. And you may know that recently there was some discussion or debate about some thing called bitter or better lesson. And basically, it's about prior knowledge about structure in machine learning. And Risotton basically argued that we just use general method that leverage computation. So, and I think one strong example is the AlphaGo. You know, AlphaGo 0, Alpha 0. So those systems, they don't need any human knowledge. They just follow the rules and they just follow the self-play and do the general policy iteration, and gradually they can find the very strong solution. So Risotton argued that this kind of general method and using the computation will be very important in the future for AI. And before that, people using all kinds of heuristic approaches and all kinds of human engineering to do all kinds of those manual things. But finally, say AlphaGo, they discard all those techniques and they can do very well. But some people don't agree. For example, Ronnie Brooks from MIT, he mentioned something like human ingenuity are pretty important. And for example, when we design CNN, we need human ingenuity to do that. And when we design, say, neural architecture design, we need human ingenuity. And there are, and also talk about, for example, the Moore's law doesn't work anymore, and so the computation power won't go as before. But so Tom Dieterich summarized something like both of them are correct in some sense. For the AI system to go, I think we hope to find some general way, for example, meta-learning. Using this meta-learning to help us find some good way to do this learning task, and try to leverage the computation. But in some, for example, the AlphaGo, we can achieve very good result. But for many problems, for example, for the recommendation system, I think it's not at that stage yet. So probably we need more human effort to make the system work. But at some time, maybe we can find some good way to do this kind of general method. So I think one is more strategic, one is probably more tactic. So, but they are basically talking the two sides of this problem, and it also depends on the stage of the problem. For AlphaGo, for Go, I think it's already we are at the stage to have some general method to do that. But even for AlphaGo, we are not sure whether it has achieved the optimal solution yet. Maybe in some time later, we can find some better solution to achieve better results or closer to optimal. But for problem like, say, recommendation systems, we probably still need some human ingenuity to do better work. Okay, there are also people talking about say system 1, system 2. Basically, is the AI community borrows ideas from psychology, and we especially help the professor in psychology to achieve some Nobel Prize in economics. Yeah, so this is from the some general or high level ideas. But good thing is people, especially from DeepMind, they make those work in DeepIR, and basically they are talking about, say, sample efficiency and inductive bias. And what they did, they use something called episodic memory and the meta-learning. So they put those ideas to work, and they can they want to learn some fast algorithm, say, for example, in inference or even in training, but they learn those using some slow method. For example, they have two levels of reinforcement learning for the meta-learning algorithms. And the inner level, they learn something in particular the inductive bias slowly and try to identify some pattern from the data. And once those patterns are identified, and they can use much less data to adapt to a new environment. So that's the idea of reinforcement learning, fast and slow. Okay, causality, that's a big topic. I basically just mentioned that, but that's a important topic for reinforcement learning for AI. And interpretability, that's also important. Yeah, that's also an important topic. Yeah, there are people talking about guidelines for reinforcement learning in healthcare. Maybe that's also helpful for other field. Yeah, so basically they talk about people need to access to all data influencing decision making by, say, doctors for the healthcare problems, and we need to think about the effective sample size, and we need to interrogate the error and the policies, and so the policy will behave prospectively as intended. So this is, I think, is about the safety, about the interpretability, those issues. And this is about do no harm. So it's, for the doctors, they need to take a walk. So I think maybe for AI people, people are talking about ethics. I think this also, apply to RL to AI. So it's not only about healthcare, but the general principle is also important for the future, human being, for the AI technology and RL in particular to coexist with human beings. Okay, there are also discussions about why AI, for AI startups, what kind of issues and what kind of say potential ideas to make AI more successful in the say startups. And they mentioned something like, say, low gross margin, like scaling issues, like weaker defensive modes, like the AI system is both software and the services. For softwares, for example, like internet, like many internet apps, we created and we put it there, like like say Clubhouse, we put there and people use it, and it's easily to scale up to for many people to use it. But for services, that's some people may how to go there. Especially some people may how to go to the customer site and do something for the services. So AI at this stage, AI is still not yet to the stage of just calling APIs. So it's not like software. It's not so much like services. So it's kind of a mixture. So we need to think about those things when we, especially when we do when we do some real system. Especially we want to do startups. And they gave some suggestions. So if you're interested, there's a blog about this. It's about yeah, there are yeah. So basically, to try to reduce the model complexity, try to reduce the data complexity, try to plan, the variable cost. It may changing very much, and to embrace the fact that AI is kind of service, not a software, and plan for changes. I build defensibility. Yeah. So okay. And Andrew Yin also gave some talks about the bridging AI's POC to production gap, and he mentioned like say small data, like generalization, like a model trained may not work in practice. And
Dr. Lee? I think there is a network problem.
How's that? Is that better?
Yeah, now it's better.
Hello. Okay. Yeah. So yeah, Warren Powell, he talked about, there are several concepts. There are, actually different communities. You can see these are big communities. For example, IR, for example, MDP, for example, optimal control, stochastic programming. So he argued that these terms, they work in some sense isolatedly, but in some sense they are dealing with similar problems. And he proposed something he called sequential decision analytics. But interestingly, he recently wrote a book. The title of the book is a reasoning on the stochastic optimization. But especially you are mathematics oriented or theory or algorithm oriented. I think his work is interesting to check. His website, but his name. I think people working in reinforcement learning should know his name. Okay, so foundations. So Sutton recently gave a talk in some AI debate. Gave a 5-minute talk, but I think he mentioned something interesting that people talking about there are. So there are 3 levels for information processing. Machine learning must be understood. There are computational theory, there are representation and algorithms, and there are hardware implementation. And so he argued that AI has a little computational theory, and he mentioned that reinforcement learning is the first computational theory of intelligence. Okay, I believe this will cause some debate, but this from Sutton, and you are interested. Yeah, I think that's interesting to check. And usually, those authors gave a tutorial about theoretical foundation of reinforcement learning in Fox. Fox is a theoretical conference for computer science. And yeah, very recently, McKinsey gave a blog. I think that's a very good news. One thing I'm thinking about why reinforcement learning is not so widely applied yet. I think one reason is people still need to know, and the professionals, the experts, still need to convince other people, especially non-technical people. For example, some CEOs, non-technical CEOs, to accept this technology. And if they are places like McKinsey, if they read blogs about or articles about the promising side of referral learning, then that will be very helpful. Okay, so this is my view. It may not be correct. So, but this is my viewpoint. So, so when R will be helpful, I think when there will be big data. So the data may be from model, for example, AlphaGo. It may form a good simulator. In some cases, we may have good simulators. We presented several cases. People are trying to build simulator for access, for say autonomous driving, and for say electricity system. And or we do the interaction. You know, the interaction may be costly or sometimes may not be safely to do that. But you know, for nature science and engineering, many tasks they have clear object function and usually have a standard answer. So in these cases, it's easy to straightforward to evaluate. And so many of those kind of problems, referral learning will probably be helpful. So the if R is not used there yet, I think there are non-technical issues. You know, if we have good model state action reward, if we are clear those kind of definitions, then if R is not there yet, so I believe the problem is not technical. The problem is probably non-technical. So so we need to find some way to overcome those non-technical obstacles. But for the social science and humanities, usually people human in the loop. So the decision and the experience usually influenced by psychology, by behavioral science, is usually subjective, and we may not have a standard answer and may not easy to evaluate. For example, we mentioned the game generation, and also, you know, for example, even for the natural language processing, we have some. So, for example, a blue score for translation, but is blue score good? Is blue score a good metric for translation? It's not perfect, right? We don't know. We don't even know what's the perfect metric for translation. It's a good one, but it's not a perfect one. So there are many those kind of problems. So we need to find good ways to define those metrics, to define your function. So maybe psychology principles. That's why I mentioned those psychology principles. For example, flow. For example, this self-motivation theory. Those kind of and also the intrinsic motivation. Maybe those kind of psychology principles, or maybe other things, can help. You know, the design the reward function. You know, for referral learning problems, if we have state action reward, then the problem may not be if we have data, right? Data is an important issue. So if we have those things, then technically we can basically solve the problem. And whether it can be adopted by the community, then maybe that's the non-technical issue. Okay, so application will be everywhere. So R solves the sequential decision-making problem, and R can help automate previously manually designed strategies. This is a graph summary, many problems, and I put some resources. Okay, yes, something about us. Basically, we are working on referral learning for real life. We have a special issue on machine learning. We have 3 workshops, and this year we have this workshop in July. So welcome to submit papers, and welcome to join when we are ready. We are close. We have invited many very good researchers and practitioners in this field. And for this special issue, we have accepted some papers already, and they are, I think, close to the publication. For several of them, they are very close. For some of them, they are maybe 1 or 2 months away from the publication. And Chaba talked about myths and misconceptions in R. So in KDD, there's a DR day. Okay, and yeah, this is my summary about why R is not widely commercialized yet. Just now I mentioned something. For example, there's actually one thing I think is say there's no killer application yet. Although there are something, for example, recommendation system, for example, robotics. I think these are very promising area. And there are already many successes, but they are not so much killer application. For example, like say face recognition for the reinforcement learning. And there are also problems like say, I don't think there are, there are problems like the, with the implementation with the algorithm and with the theory. There are also rooms for those to improvement, but there are also many problems. For example, we don't have enough resources for reinforcement to try, and there are maybe non-technical issues. And so we need more education. And I think that's, if there are more and more this kind of workshops, and there are say tutorials, workshops, and those kind of things. And especially if there are more like the McKinsey blogs, and so for non-technical people to know the potential of the reinforcement learning, then gradually reinforcement learning can be more and more widely deployed. Okay, so yes, reinforcement learning works in many cases. There are lots of successful stories already. So reinforcement learning, I think the time is coming. It may not be like the AlphaGo or like the say deep learning, say ImageNet in several years ago, but it may go slowly. Like say, I think rec system is slowly taking this, somehow slowly, but I think there are already good stories. Okay, there are more references. So basically, yeah, this is my talk. Let me see. I think there are questions. Okay. Okay. Okay.
Okay, thanks for the great talk. Any questions from the audience?
Yeah, I know this is a big summary and big overview. So hopefully I can provide some pointers. So if people are interested in some topics, this is an easy way for you to check something. And yeah, hopefully I can, especially for some non-technical people, I can convince you that reinforcement learning will be very promising.
Yeah.
So in recommendation systems area, what are some promising directions for reinforcement learning?
In recommendation systems, yeah, to be honest, the workshop chairs, I think they are more expert than me in this particular topic. If for me, promising, there are several angles, right? It's for research, it's for say startup, maybe for say deployment or something. If for example, if you are talking about, so for example, for research, I would like to say, I also mentioned, for example, interpretable maybe important, right? Sometimes maybe important. For example, if you want to report these results to your, say, to a manager or to the CEO, this month we achieve 1% improvement for the click-through rate using this reinforcement learning. Why is it works? Why it doesn't work? So we need some interpretable or causality to present to those, especially those higher management, about why this technology works. So I think the causality and interpretable should be important, especially for recommendation. So recommendation, I think, don't care so much. For example, comparing with healthcare or autonomous driving, safety, although it's important, but not so much. But I would like to say interpretability and causality will be important, interesting issues for recommendation systems. But that's I think academic point of view. Yeah.
Okay. I think due to the time limit, I think let's thanks to our speaker, Dr. Yuxi. Thanks for the great
Yeah,
talk.
thank you. Yeah, thank you for the audience and the organizers.
Yeah, thank you. Okay, I think the last talk is a paper talk from Zhengxing Chen from Facebook AI. Zhengxing, it's yours.
Hey, hello. And let me start sharing my screen. So I need to rejoin the Zoom because the share screen permission.
Okay.
Yeah. So can you see my screen?
Yes.
Okay. Yeah. Okay, so let's get started. So my name is Zhenxing from Facebook Reagent team. We are doing applied reinforcement learning. And it's great that Jason and Yuxi gave a great overview of the reinforcement learning landscape. And today I'm going to talk about a feature analysis tool for batch RL datasets. So this is a work mainly done by my former intern, Ray Yang, who started reinforcement learning at Northeastern University. So our reinforcement learning has become more and more important. And like the industry has gradually picked up reinforcement learning in recommendation systems, in parameter tuning, things so on and so forth. And in traditional reinforcement learning, as we see in video games and board games, reinforcement learning agent usually interacts with the environment continuously. So they observe like the game states and take some action, observe some rewards, and then constantly update their policies until like their network become more and more powerful to play through the games. But usually in the industry, we have a different story. Right? In industry, sometimes it is very hard to update policies in a real-time manner. So more often we have this following paradigm, which we call batch offline RL. So maybe some product team or some data scientists, they curate big data sets from past user historical data. And using that data set, they train full offline RL policies like DQN, like software actor critic. So during the training, they can train for many epochs, but the RL agent never interacts with the environment. And once the agent finishes training, they deploy policy online and check like in an A/B test setting whether this policy can bring more revenue or more user engagement. So this is an offline setting, and it is very common in the industry. So typical offline data sets is like a Hive table or similar thing, where we have multiple columns containing necessary data for training RL policies. So as you can see, this is one example like used for reagent. So we have one column denoting what's the MDP ID, which usually denotes the user identity. And we have state features, which in recommendation system, usually state features are user features. And the action column, depending on specific application, action could be discrete action, like sending notification or drop notification, or some continuous actions, like maybe a vector of some float numbers. So as you can see, we usually this data set is collected from product teams, and they usually have less RL expertise. So what the problem of the data is that many times we see that there are like abnormalities in data set, or like the data set is not good for applying reinforcement learning. So here I just list a few problems we often see from our like industry experience. So one is that the product team collects a large number of state features, but most features are not very relevant to what they strive for optimizing. So for example, they usually draw in user features from different tables. But if they just want to optimize revenue, for example, only a few features might be relevant for revenue optimization, and all other features will be a waste of space and may cause our policies to learn more difficult. And another problem is, like we said, usually the product team don't know whether a problem is a contextual bandit problem or a sequential multi-step optimization problem. So I remember Jason gave a good example earlier in his talk. So let's say we want to send coupon to users, and the product team usually think, okay, maybe we can optimize the coupon sending policy such that in the long term, users could have more generated more revenues. But in fact, often maybe user only click no more than one time. So this problem is hard to be formulated as a sequential problem, but a bandit problem at best. And the product team usually just collect data and they wish to apply RL, but sometimes they don't know whether to apply contextual bandit or multi-step sequential optimization. And also, it's possible that the action they collect is not really effective. The action they collect is not designed very well. So like it's very hard to learn an effective policy to optimize the report they try to optimize. So our goal is to develop a tool for automatically drawing insights for people, either with expertise in RL or not. And we will tell them whether their data set or their underlying problem formulation corresponds to a well-defined Markov decision process. So I want to draw a comparison with existing offline RL research, because existing batch offline RL research usually assume you have an MDP, you have a known MDP, and they just study maybe learning convergence or study exploitation, exploration. But before all this happened, like for the RL practitioners, it's very important to know whether they formulate the problem correctly. So here's how we solve the problem. So we start from the definitions of Markov decision process. I believe most people know in this workshop, but let me repeat quickly. So in a Markov decision process, we have state space and the action space, and the state, and like there's a state transition function, which is the function of current state and action. And we also, there is a reward function, which is also a function of current state and action. And the goal of an RL policy is to optimize the long-term reward. So this is the basic idea of Markov decision process. And once we have a data set, we want to draw insights on this data set. The first step we do is to train a word model for modeling state transition and the reward function from the given data set. So we pick one very classic model-based RL model, which is called word model. And this word model, in essence, is just use a deep learning neural network to predict rewards and the next state using the input of the current state and current action. And the loss function, as you can see, it merges two loss functions. One is for reward prediction, and the other is for transition prediction. And once we have the reward model, we are going to ask two questions. The first question is that, is there any state feature that can predict rewards well? So how can we measure the predictive power of a state feature? So for each state feature, we mask them. We mask each state feature, and we train a word model without that feature, and we get a reward prediction error, MSE. And this reward prediction MSE is a number that can quantify whether a state feature is important for predicting reward. Because if a state feature is very essential for reward, then training a word model without that feature will definitely make reward prediction less accurate. So we use this use this method to quantify whether a state is important for reward prediction. So one decision we can make, one insight we can make is that if no state feature can help predict reward better than a dummy state just like we inject the dummy state that it has nothing to do with the reward. So we can know, like, if there's no actual state feature that can help predict reward, then there's no reward contributing state feature. Then this problem is a bandit problem at best, because you can just discard all the state features at all, and the state space is not designed effectively for the problem, for the reward you try to optimize. And if we have identified some subset of state features which are reward contributing, then we ask the next question. So is there any state feature that is sensitive to actions? So action sensitivity means that if we shuffle actions and we look at the word model's next state prediction, is there any state that will be changed very much? Or is there any state that, like, even you shuffle action, the next state prediction change very little. If no state is sensitive to actions, meaning if like no state can vary a lot, even you shuffle the action as the input to the reward model, then this kind of tell us that your action space is not designed effectively because your action cannot control the state, and that's learned from the reward model. So to be more clear, at least I draw this decision tree as the procedure of our feature analysis tool. So we first, the first step, like I said, is reward contribution analysis, and then we look at whether there's any state feature that is important for reward prediction, and if there's any, we then conduct action sensitivity analysis. And if there's some overlapping between reward contributing and action sensitive state features, then we can conclude that this data set or this problem formulation is potentially for batch RL. And then we can move on to really training RL policies. So is there any question so far? Okay. So we have some results on constructed environments and some like real world environments implemented in June. So for simplicity, here I just report some constructed result, like results on constructed environments. So we construct several different environments with different causal relationships between action, state, and rewards. And in like for example, in the right environment, in the second row on the right, this environment we create some data that there's discrete actions, two actions, A0 and A1, and there are 10 state features. And the state transition we design is that it is a stochastic counter. Whenever we have action 1, then the states could be added 1 with some probability, and that different states have different sensitivity to the action. And the reward function we design is like if the first state is more than 4, reaches more than 4, then we give the environment 1 reward. Otherwise, the reward will be 0. So we just like take random action and observe the reward and next state and collect all this experience into a replay buffer, and let the reward model to train a reward model. And after that, we apply our feature analysis tool to see if the results make sense. On the left, we can see that for reward contribution, we can see the first state is very important for predicting reward. That's as expected because we deliberately design that the reward is relevant to only S0. And on the right, we show the action sensitivity, which means that the first state feature is most sensitive to action because depending on the probability we design, the first state will be mostly deterministically added 1 if the action is 1. And for all the other actions, there will be decreasing sensitivity for action. So from the plots from both sides, for this specific environment, we can conclude that there is some overlapping between reward contribution and action sensitivity, which is just the feature, state feature 0. And this shows that this gives us the conclusion that this environment is suitable for RL, and the practitioner can go ahead and really train RL policies to optimize rewards. So we also design other environments, such as maybe we remove the causal relationship between A and S or S and R, and we will find that there's no overlapping between reward contributing state features and the action sensitive state features. Then we can conclude that this data set is not suitable for applying RL, because either there's no action cannot control states, or state cannot predict rewards. And also we can use this tool to even filter out useless features. So in this case, we can actually filter out all the features from 1 to 10. So with such tool, if we apply on real world data, greatly reduce the feature space of states, and as a result, we expect that the RL policy will be converge more efficiently, and also when serving the RL policy will be more efficient. So there are some limitations of our work. First of all, the most important one is this is a heuristic-driven approach, and there are many corner cases that we cannot cover, or we cannot conclude definitely. So one such example is if there is some hidden confounding variable between S and R, then our feature tool will suggest this problem is suitable for applying RL. However, this problem still not be optimizable because there is a hidden variable, but the action really could not control that hidden variable. And the second limitation is that the word model can still be improved. They may not learn very well if the data distribution is skewed or under high dimensional data. So this is something we can improve in the future. So as summary, we introduce a heuristic-based feature analysis tool for validating problem formulation and data collection in offline batch RL setting. And we are considering open source data as a self-contained module very soon. That's it. Thank you.
Okay. Thanks for the great talk. Any questions? Zhengxin, what's the training efficiency of your model?
So can you be more specific? What kind of efficiency are you talking about?
I mean the training efficiency. What the resources you need and how long time you need?
Yeah, that's a great question. So we use the same infrastructure that trains RL policies to train word models. Mm-hmm. So we don't expect we need extra more advanced infra for training the word model. We use same like maybe GPU machines, and we use same Spark data set, like Spark to read data from a database. So yeah, I think the infra cost is not any different than training an RL policy.
Okay, thank you. Other questions? If no questions, let's thank our speaker, Zhengxin. Thank you for the great talk.
Thank you.
Okay, that's all the talks of our workshop. And thanks for the great talk from all the speakers. And thank you all the audience for attending our workshop. Thank you.